Okay. So we got up there. I have graded your submissions for the project. I'll hand those back in a little bit. The reservoir sizing draft submission Monday the 25th. That's after you come back from spring break. And then the final submission, I think I'd earlier guessed that it was April 5th, but I was thinking of a different class, different project. Our final submission for the project is the 12th of April. Your next homework assignment, homework 9, is due on Friday, and that's a pretty easy assignment. If you would like to submit that via email, I'll be happy to take it that way, or if you want to submit it early. It's just talking mostly about critical debt, things that we've talked about in previous classes and a little bit more today. We're going to continue a few little side items on the project by reviewing some concepts related to the time value of money, talk about the project finance aspect, and then we'll get into total energy and specific energy, some applications related to that. So, any questions on the announcements? Okay. Well, in the project assignment description, it mentions that you need to find out the cost of the project in the present. And so that's going to consist of the pipe and reservoir costs in the present, and then from that find out what the quarterly payments are for the municipality or the utility that's borrowing money to finance it. And you have to find out if they were going to try and spread the cost of the project out over 5, 10, 20, 30 years, how much are their quarterly payments going to be? And then based on those quarterly payments, what's the annual cost either on, well, both. You have to consider it both on a per customer basis and then also on the basis of flow rate, if the cost was based on demand. And the reason for these two different analyses is to illustrate that if it's on a per person basis, then a residential user may be getting in a bad shape. You know, they use a very low flow rate compared to a hotel or a hospital. And so looking at water costs both of those ways. I've already provided the link to the Bloomberg municipal bond rate site, but it doesn't have rate data, I think, for 20-year bonds, and this site does have 20-year bonds. I don't think either of them have 15-year bond interest rate data, and so you can exclude that from the report. But remember, in the time value of money, what you're trying to do in finding an annual series is find out what's the recurring payment going to be at a certain interest rate for a certain present value, the present value being the cost of the project that you've summarized based on the pipe and reservoir costs. And so here is the idea behind an annual series, and the equation and the corresponding table lookup factor. For the project, I'd like you to solve this by hand, although you can confirm your calculation with the Excel payment function. But there will only be, you'll have to solve this A to P conversion equation 4 times for the 5, 10, 20, and 30 year, and then multiply it by the present value to find the annual cost for each. And by the way, when it says A, that'll actually be the quarterly payment. What you're going to do is if it's a 5-year repayment and you're doing quarterly payments, then N would be 20. And so A means annual series, but what it really means is a periodic payment. So for the 30-year repayments, if it's quarterly payments, 30 years, there will be N equals 120 would be the total N that you use. And then I is the interest rate per period. And so when you go to the interest rate website, if it says that the 30-year bond rate is 3% per year, then the I you should use in there is 0.03 divided by 4, because there are 4 periods per year. So just a couple of items to refresh your memory about what you've hopefully retained from Engineering 221. Anybody not had that class yet? You can come see me if you've got questions once you give that equation a try. The main things is N is the number of payments, and I is interest rate period. So if it's 3% per year, then I would be 0.03 divided by 4, because we're doing quarterly payments. There's a function in Excel that you can double check your calculations with, and the function is this payment function. And as you start entering the payment function, it will prompt you for what it wants to see in certain fields. So the rate that you would put in would be the interest rate per period. NPER, that's N, the number of payments. And PV would be the amount that you've estimated the present cost of the project to be. And then these fields that are in brackets, those are optional fields that you won't use. You can have it calculate the payment either based on a present value or a future value. We'll be doing it based on a present value. And then this type function has to do with whether payments are made at the end of the year or the beginning of the year. So you can just ignore those last two functions. It's just the first three fields that you'll need to fill in. Like I said, if you haven't had Engineering 221, feel free to come see me if you need a little bit of help doing those finance calculations. But I would like you to just by hand do those calculations and include it in your final report. Don't type them into Excel. Do them by hand. It's easier to grade them both, grade them and to prepare them. Okay, a review of what hydraulic depth is. Remember that hydraulic depth is a way of converting a non-rectangular channel into what its equivalent rectangular channel depth would be. And what we've seen previously is a rectangular channel where the bottom width b, lowercase b, is one thing, but the top width changes as a function of how deep the flow is. And the deeper the flow gets, the taller, the wider the top width. And the top width is a function that goes into the Froude number calculations. And in a rectangular channel, because the area is going to be T times Y, then the hydraulic depth of a rectangular channel is just its physical depth, Y. So hydraulic depth is the same thing as its actual depth. Now, one sort of a simplification that we know is that if the channel is very, very wide, then we can assume that its hydraulic depth is equal to its actual physical depth. And let me illustrate why that would be. So let's say we have a trapezoidal channel, but it's very, very wide. Well, in this case, the area associated with the sides are going to be insignificant compared to the rectangular portion of the area. And so in a case where it's very wide, the hydraulic depth is essentially the same thing as its actual physical depth. And by very wide, what we usually mean is that the width is more than 20 times the depth. That's the commonly established criteria for when the width is considered very wide. A lot of things will simplify. We'll come back to this issue of a very wide channel again in the future, but some of our formulas will simplify if we can just ignore the contribution of the side, both its wetted perimeter and its area. It makes calculating certain things quite a bit easier if it happens to be a wide rectangular channel. This figure was introduced in the last class period where we graphed specific energy as a function of flow depth. Remember that the water can go through a channel at a very high velocity where the depth will be low, and so that would be supercritical when it's below the minimum specific energy. The depth is below that critical depth. If the depth is greater than the critical depth up in this region, it was subcritical flow. But what we saw from this figure is that you can have, for one specific energy level, two different depths of flow. And let's just take the case of if we have a specific energy. What is the specific energy when the depth is 0.5? So when the depth is 0.5, we can find the energy, E, is simply 0.5 meters. That's the Y part of it. And this is the example that when the specific energy is 0.5 and this rectangular channel is, the flow rate is 10 cubic meters per second, the width is 4. So for this condition, we can have the flow rate, Q squared, so that would be 100 and 2 times 9.81 meters per second, and now the area squared. 4 times 0.5 squared. The total energy for that is 1.774 meters. And so there is some other depth that has that same energy level. So 1.77, we're talking about, here is the energy, 1.77. The depth is 0.5. There's this other depth up here that has the same energy level. And so we're going to try and calculate what is the alternate depth. We can solve the specific energy equation. All right, so the alternate depth is where we say 1.774 meters is equal to y plus 100 divided by 2, 9.81, 4y squared. Okay, so in the area term, the width b is still 4, but we don't know the depth y. So the unknown is both in the formula for the area and the depth itself. So we know E, we know Q, we know G, but what we don't know is Y, and one of the components of the area is also Y. So when we combine it, it's 1.774 is equal to Y plus 0.3186 divided by Y squared. Or in other words, 1.774 y squared is equal to y cubed plus 0.3186. All right, that is y cubed minus 1.774 y squared plus 0.3186 is equal to 0. So with your calculators, find what are the roots to this equation. What are the 3 values of y that satisfy this equation? While you're doing that, I'm going to hand back these network designs, and we'll talk about it a little bit later. Everybody get theirs back? Okay, so those three roots should be negative 0.3842, 0.5, and 1.658. We can immediately dismiss the negative depth. The water can't flow at a negative depth. We already knew 0.5 was one of the possible roots. And we'll go over the design stuff a little bit later. And so the alternate depth that we're looking for is 1.658 meters. So that is the other depth. And if we refer back to the chart, it looks like that's about accurate. You know, with the energy level, we were looking for 1.774. So we were trying to find out the alternate to this depth of 0.5. So it goes up to here. We can go over and find 1.66 meters. That's the alternate depth. What we've just done assumes that water can go between those two depths without any energy loss. And there are transitions where actually there's a lot of energy loss through the jump from one depth to another. And in future examples, we'll address how to calculate the energy loss in a jump to the alternate depth. But in this case, we were just assuming that it's strictly a jump between the two conjugate depths. Any questions about this example?
So what determines what depth it's going to be then?
The slope.
The slope.
Yeah. Yeah. If it's at a really steep slope, then it would be at the supercritical depth. If it's at a mild slope, it would be at the subcritical depth. Okay, well, let's talk about critical conditions a little bit more. Froude number equal to 1 is the cutoff criteria, and this will give a little bit more information on where that Froude number criteria comes from. At minimum specific energy, where the point is the lowest, so in this example that we had previously, the minimum specific energy corresponded to a depth, I think, of 0.866 meters. And what that means is that the depth, the specific energy is not changing at all at this point. You know, before that, changes in depth were either increasing or decreasing the specific energy. So we're talking about the slope of this. When we get to the minimum specific energy, the change of depth does not affect E any longer. And E does not change with Y. So straight up and down, vertical line there at the minimum specific energy. And so if we look at the equation for specific energy, it's the depth plus the flow rate squared divided by 2G A squared, and take the derivative of that with respect to Y, we get over on the right-hand side the term dA dy. And what that means is that we consider a differential element of area in a channel. The dA is some incremental depth dy multiplied by the top width. And so that's what we're talking about. That's why the top T formula is in the Froude number, is because as the water is getting deeper, as there's an incremental increase in the flow depth, this semi-rectangular element depends on the width at the top of the channel. And we're doing a very, very small incremental area, so that the fact that it's a little bit wider on top compared to the bottom doesn't matter, because it's such a small increment there. Those two widths are essentially equal. And so if the energy isn't changing with respect to an incremental change in Y, meaning that we're trying to find the critical point where the slope here is 0, so that is where we say that this constant of 1 is equal to Q squared times the top width, G8 cubed. At critical conditions where we're at the point of minimum energy, then those are equal to 1. And so where the Froude number is less than 1 is the subcritical conditions. So if we have a positive slope, that's what gives us subcritical conditions. Negative slope is what gives supercritical conditions, once we've taken the derivative with respect to Y. This equation is essentially the previous one, the Froude number equation, just rearranged in terms of when we have a critical top width, a critical depth that gives us critical area. And so regardless of what the channel cross-section looks like, this equation will always be valid. Now there's a simplification that I almost hesitate to even show because students continually misapply it, but here's the shortcut anyway. If you've got a rectangular cross-section, the critical depth can be found with something called the flow per unit width. And so if you divide up the total flow rate by the bottom width, you can find the flow per unit width. And then finding the critical depth is just as easy as the flow per unit width squared divided by g to the 1/3 power. So that's the shortcut, the simplification. So before we apply that simplification, let's just try out the way that's always valid and then compare it. So we want to find the critical depth. This equation rearranges q squared divided by g. 4 is the bottom width, yc cubed divided by the top width when conditions are critical. So t is 4, and so that is y c squared. YC is just so B is both a function of it goes into the area. The bottom width of 4 goes into the area, but then the bottom width and the top width are the same. They're 4 because this is a rectangular channel. If it was a trapezoidal channel, they wouldn't be the same. All right. So the other approach, to use that shortcut method that's only valid for a rectangular channel, we first need to start off by finding the flow per unit width. And so the flow per unit width, lowercase q, is the flow and the width. And you can only find a proper flow per unit width for a rectangular channel. You can't say what the flow per unit width is for a trapezoidal or a circular channel. And you'll see these units 2.5 meters squared per second. And the reason why it's meters squared per second is if you've got cubic meters per second, 10 cubic meters per second flowing through 4 meters, what we're trying to do is we're saying we know through this entire 4-meter section, 4 meters total width, there is 10 cubic meters per second going through the whole thing. So how much is going through each 1-meter section? It's 2.5 meters squared per second because it's cubic meters per second divided by the meters. So that's why the units are a little bit unusual for the flow per unit width. Once we know that, we can find the critical depth. Y sub c is just going to be Q squared divided by G to the 1/3 power. So 2.5 meters squared per second squared divided by G, 9.81 meters per second squared, the 1/3 power. So that is 6.25 meters per second squared divided by 9.81 meters per second squared, the 1/3 power. And that gives us the same answer, 0.860 meters is the critical depth for that rectangular channel. All right, so one last emphasis that this equation should only be applied if the channel is rectangular. If you have a trapezoidal channel or a circular channel and you're trying to find out what the critical depth is, then you should use the full version of the Froude number equation and solve for the top width as a function of y. Yeah.
So if it's the really wide channel, we can still use the...
Yeah, if it's really wide, we pretend rectangular. Yeah. Good question. In a previous class, we tackled the case of a pipe that's flowing full. And there's a nomograph that makes it easy to find the required dimensions of a pipe, whether it's the cross-sectional area or the flow depth or the flow rate. There's a nomograph that will allow us to sort of graphically solve these things. And to illustrate how the nomograph is used, I've selected this pipe where the diameter is 0.9 meters and the discharge of 0.566 cubic meters per second. What's the critical depth? And what we have to do in the normal way, remember, is use those geometric parameters and find the angle theta that the water surface makes with the center of the pipe. So the normal approach for solving a problem like this is to try and find out the unknown depth y as a function of that angle. And so the first thing to do is trying to find the angle based on the fact that we know the diameter and the discharge and putting it into Manning's equation. So let me illustrate how easy the nomograph can be if we start the hard way. This is the hard way. What we would have to do is first, for Q is 0.566 cubic meters per second. The diameter is 0.9 meters. The area is going to be d squared divided by 8 theta minus sine theta. And so that would be 0.10125, substituting in the diameter of the pipe that we know, times theta minus sine of theta. The top width is going to be d times sine of theta divided by 2, so 0.9 sine of theta divided by 2. And if we substitute that into the Froude number equation, where Q squared times T, G area cubed is equal to 1 for critical conditions. So we're trying to find out what is the depth that will make the Froude number equation equal to 1. The flow rate is known, 0.566 cubic meters per second squared. The top width is a function of the angle, 0.9 sine of theta divided by 2. G is a constant, 9.81 meters per second squared. And now the area is a function of the angle as well, 0.10125 sine of times theta minus sine of theta is equal to 1. And if we put that into a solving calculator, radians mode, to find out what is the angle that makes all of that true, is an angle of 3.09 radians, 177 degrees. And so it's almost half full. And once we find that angle, we can put that into the equation for flow depth y as a function of the angle. Y is d over 2, 1 minus cosine of theta divided by 2. And so our depth is 0.9 divided by 2, 1 minus cosine of 3.09 radians divided by 2. And that gives us a depth of 0.44 meters. And so that example illustrates the process of how you go from some specified discharge and a pipe diameter and how we ultimately can find the critical depth, y sub c. So this is critical depth. In the example, no pipe slope was specified because it's not asking what will the water depth be in a certain situation. It's asking what's the critical depth. Now the critical depth can be achieved if we lay the slope out on the critical slope. But there's an infinite number of depth possibilities depending on what slope is actually used. It could be a supercritical flow, it could be subcritical, but this, for a certain flow rate and a certain pipe diameter, this is the critical depth. And we can compare the actual flow depth to this critical depth to know if conditions are subcritical or supercritical later on. But there's an easier way. And the easier way uses the nomograph. And then there's a nomograph prepared for both a trapezoidal channel and a circular channel. And over here on the y-axis, I want to point out that this y sub c to d is for the circular pipe. And for the trapezoidal pipe, what you'd be looking up on the y-axis is t times y sub c divided by b. And so there are different things on the y-axis depending on whether you have a circular or a trapezoidal pipe. We're going to do the calculations for a circular pipe.
That trapezoidal one says T y sub c over b?
Yes, t y sub c divided by b. I realize that's small. I think that that figure comes from your text, and it's much bigger in the text than it is on your slide handout. Okay, so the easy way, using the nomograph. A little bit less accurate since we're trying to pinpoint a place on the chart. But we start by calculating this z factor, q divided by g to the 0.5 power and d to the 2.5 power. Okay, in this case, 0.566 is the flow rate, and 9.81 meters per second squared to the 0.5 power, and then the diameter 0.9 meters to 2.5 power. And that gives us a z value of 0.235. So with that z, we now go to the nomograph. You notice on the x-axis is a logarithmic scale. And so what the logarithmic scale means is that you have to go more than halfway the distance before you get halfway the amount. So 0.1, 0.2, 0.3, 0.4, 0.5. So 0.5 is pretty far to the right of the center here. We're looking for 0.235. And so that's 0.1, 0.2. Now to get from 0.2 to 0.3, we have to go a little bit more than halfway to get the actual halfway mark between them. So maybe in the middle between these two would be the 0.235 that we're looking for. So we go up to the circular, and that happens to be pretty luckily where it's crossing the that axis there. That's why I chose that particular flow rate, I think, just so it'd be easy for us to notice that it crosses here. We go over. Okay, so this was now 0.1, 0.2, 0.3, 0.4, 0.5. Y to C divided by D is equal to 0.5. And we got this from the nomograph. That's telling us that the critical depth relative to the diameter of the pipe is 0.5. So the critical depth is 0.5 times the diameter of the pipe, 0.9 meters. And that says it should be 0.45 meters is the depth. And that's very close to when we had calculated it, the full-fledged, full precision hardware. The difference being probably our ability to eyeball some value off of the figure. Any questions on this critical depth method? Okay. Critical slope. So, what governs the actual depth that it's going to flow at is the critical slope. Is the slope. And the critical slope is that slope that ensures that there is a critical depth that's achieved in the channel. So we've got a trapezoidal channel with a bottom width of 3, side slopes of 1.5 to 1, carrying 186 cubic meters per second. Find the critical slope. I know we've been hitting these examples awfully hard and fast today. There's just a lot of ground to cover. So we'll do this example, and then we'll talk a little bit about the pipe networks. So we've got some flow depth Y, 3 meters on the bottom. The side slopes are 1.5 to 1. The area, remember, our formula for that, B plus Ty times Y. The wetted perimeter is V plus 2Y times W, where W is 1 plus T squared to the 0.5 power. You could derive all these just by looking at it and figuring out, the wetted perimeter and the area, top width manually. If you don't have access to the equation table, okay, in our case, the T is 1.5, and so W is 1.803. All right. If we want to find the critical depth, that's going to be Q squared times T, G, A cubed times 1 is equal to 1. 186 cubic meters per second. The top width is 3 plus 2 times 1.5 times Y. That's the equation for the top width, where the bottom width is 3. 9.81, and now the formula for the area, 3 plus 1.5 times y to the third power. So that is the formula for area. And we set that equal to 1. Okay, so we use our solver and find that the depth of flow is 4.121 meters. That's the critical depth. And we're going to use Manning's equation to find out what slope will give us that critical depth. And remember, Manning's equation is Q is A divided by N, hydraulic radius to the 2/3 power, slope to the 1/2 power. And we can rearrange that to solve for slope. Slope is N times Q divided by A times hydraulic radius to the 2/3 power, all of that squared. Now, when we have this critical depth, the wetted perimeter will be 3 plus 2 times 4.121 times 1.803. So the wetted perimeter is 17.858 meters. The area is 3 plus 1.5 times 4.121. The area is 37.837 square meters. We're going to substitute those values in here to find the slope. Okay, the N value, concrete, gives us the N value of 0.013 times the flow rate, 186 cubic meters per second. And the area, 37.837 meters squared. And the hydraulic radius, 17. Hydraulic radius is the area divided by the wetted perimeter. And so that's 37.837 square meters divided by 17.858 meters. So the hydraulic radius is 2.119 meters. And that's what we're going to put in here into Manning's equation. 2.119 meters to the 2/3 power, all of that squared. And so the slope that gives us critical conditions, 0.0015, that means that the critical slope is 0.15%. So that's how steep the slope would have to be in order to cause critical conditions through that trapezoidal channel at a flow rate of 186 cubic meters per second. All right, well, regarding the project, I think that in general, most people did a really nice job optimizing the networks. In some cases, it was difficult to read the printout. I think that some people printed directly from WaterGems and other people took a screenshot and then pasted the image of that screenshot into another document. I'm going to record a brief video that shows you how you can print out directly from water gems so that it doesn't become pixelated and blurry. So that, be sure that when you do your final submission for the full report that it includes the printout directly from the program and not copied and pasted. Another aspect is that in some cases the reservoir elevation wasn't provided on the map, and be sure and annotate the reservoir elevation. And also another thing that needs to be annotated is the demand out at the junctions. And that's something that I can include in the video that shows how to prepare a print directly from water gems, is that it is possible to annotate the demand at a junction so that I know how much flow comes out at that junction. And in fact, to make it very clear that water's going out at some of those junctions, I'm going to ask that you manually draw, there are drawing tools inside of the program, manually draw the an arrow to indicate where the flow is coming out. Let me just start up water gems here. So they give you standard drawing tools. While it's loading up, let me just mention that the main thing of these maps is to show that you've optimized the network, that the pipes are as small as they can be without being too small. And too small means that under maximum demand flow that the pressure is below 240. And so under maximum demand flow, if your map has lots of junctions that are still in 500, 600 range and none of them that go down below 300, then that's an indicator that probably you could make certain pipes smaller than they are right now. And likewise, under the static flow conditions where there's no flow out or very, very low flow rate, what I'm looking for there is that none of the pressures go above 850. But if you have a bunch of junctions where the highest pressure on the map is 750, then that would tell me that the reservoir isn't high enough. That if you take the reservoir higher, then it might allow you to make some of the pipes smaller under maximum flow demand. And so the two extremes are, you've got to be close to 240 under maximum demand and close to 850 under no demand. All right, so in the program, if you have a network, I see we're almost out of time, so I'm just going to include in the recording, I'll include not only how to annotate the demand at a junction and print from within the program itself, but also how to draw your own little arrows to make it absolutely clear that flow's coming out at certain junctions. So if you've got any questions, please feel free to stop by during my office hours and let me know, and I'll see you on Wednesday.